Okay, you guys, number 4 on 4.4. You have a question about that? Okay, it says the topic is an absolute value of nonlinear functions. So here I'm going to give you a different function. And the function they're giving you is a function called, this one's probably a sine or a cosine function. We're actually studying right now in Secondary Math 3 and in my pre-calculus class. You guys will do these next year. But this one's actually a cosine function. And it just goes back and forth like this, right? Something like that. I'm not going to write it perfectly the way they did, but... What? Yeah. See those signs? You guys been seeing them around the... Yeah. My class has made these. You guys get to do it next year. Yeah, they're exactly the same because I had them do them in groups of 4. Everybody did one. Because I'm trying to teach them about the cosine and sine function, so they all had to learn the same thing.
Is the straw broken?
Okay. So when we did it, the sine and cosine function, that's them. Huh? Someone broke it. Someone. Okay. So anyway, just please listen. Okay, and so you can see how the cosine function, it's the bottom one up here. It starts up at the top, goes down below the x-axis, comes back up above the x-axis. Anyway, that's what the cosine function does. Well, it says in figure 1 is the graph of a sound wave. A sound, you can use the cosine or the sine function to model a sound wave, and that's what they've done here. The height or depth of the graph indicates the magnitude and direction f of x reaches from the norm or the undisturbed value. So the x-axis would be the undisturbed value. This is its maximum right here. This is its minimum point right here. Okay, and it's the same all the way across. Okay, in this case, that would be the x-axis that is talking about the undisturbed value or the norm. Okay, when we are only concerned with the distance from the x-axis, we refer to this distance as the amplitude. And that's what we're studying right now. In my class right now, in my Secondary Math 3 class, we're learning how to move those around, up, down, left, right, to stretch them out, to shrink them down horizontally, and also the amplitude, how high they go, up and down. Since distance alone is always positive, amplitude can be described as the absolute value of f of x. Okay, use the graph of a sound wave to sketch a graph of the absolute value of the amplitude, or in other words, y equals f of x. So we're going to graph y equals the absolute value of f of x. We're supposed to graph that right there. So I'm going to do it on the same graph, except for I'm going to use a red pen. Now, think about what we learned about all the other absolute value functions. When we took the absolute value of them, what did it do to the graph? Exactly. It made all the negative ones go up. So this part stays the same. What happens when I get right here?
It bounces.
It bounces up like that. And then this part's the same. When it gets right here, what does it do? It bounces up. Then it follows this line right here, and then it bounces up. Okay? And that's how you got it. And so you're going to write it on that line at the right. That's what it's asking you to do. Okay? Is there another question? I'm not going to do number 5 because we did some of those on that task. I want you guys to think about that one and see if you can get it. Okay, number 14. Okay, number 14. Okay, let's do that one. Assume that x is greater than or equal to 0. Okay, in other words, we're taking the absolute value, or we're taking the square root of positive numbers. So it gives you this equation right here, square root of x plus square root of x cubed plus square root of x to the 5th plus square root of x to the 7th plus square root of x to the 9th plus square root of x to the 11th. How far does it go? 15. Plus square root of x to the 13th plus square root of x to the 15th. It says use rational exponents. What are rational exponents, you guys? Does it have to do with this? Okay, what?
What
Well, no, that's not. When it says x is greater than or equal to 0, what it meant is that all these numbers have to be positive. X represents a positive number because you can't take the square root of negative numbers and get a real number. Take the square root of negative numbers, you get an imaginary number.
Yeah,
So it's just telling us that all these are positive numbers. Okay? So, but how would I write the square root of x as a rational exponent? Roger, what do you think? How do you write square root of x as a positive exponent? I mean, as a rational exponent. That's right. Okay, Christian, how would you write the square root of x cubed as a rational exponent? X to the 3/2. Okay? Jessica, how would you write square root of x to the 5th as a rational exponent? Oh my word.
You didn't even get her name right either.
Jerica. Justine. Okay, thanks. Sorry. Huh? That is right. Who else do I get mixed up with their sister or brother? If I taught your older brother or sister, I always get you mixed up. Jared. No, I'm just kidding. All right. What do you think, Brendan? X to the 7/2. Okay? Grant, what do you think? Next one. Okay. All right. David. What's the next one? Thank you. Okay, Jacob, what's the next one? All right, what's the last one, everybody? All right. So you guys get that. Now,
that's all you can say with that.
well, here's the deal. All of these, where the top number of the fraction is bigger than the bottom number, you can divide those into it. So we can do this. We have x to the 1/2 plus x to the 2/2 times x to the 1/2, right? Plus x to the 4/2 times x to the 1/2 plus x to the what? What's this one going to be, you guys? What's that one going to be?
2/2.
X to the, how many times will 2 go into 7? That's 6/2 times x to the 1/2 plus what? X to the 8/2 times x to the 1/2 plus what? X to the 10/2 times x to the 1/2 plus x to the what? What's the next one, Brienne? X to the 12/2 times x to the 1/2. What's the last one, everybody? X to the 14/2 times x to the 1/2. Okay, so now look, what's 2 over 2, you guys? 1. So x to the 1/2 plus x times x to the 1/2 plus x to the 2nd times x to the 1/2. You guys understand what's happening here? What's the next one? What's the next one? What's the next one? X to the 3rd, because 6 over 2 is 3, right? Times x to the 1/2. Finish that out. I'm not going to finish it. Yeah, David. We're learning about how to change radicals to rationals. Then we're learning how to break like x to the 3/2 into x to the 1 times x to the 1/2. And we're learning. Well, it says simplify. So we're simplifying. We're getting there. We are getting there. We're rewriting as many expressions as we can.
It's not
That won't work. Okay, you guys, how many of you, if you just add these all up, you can't do that because these are plus signs in between. They're not times signs. Okay, well, I'll show you what it simplifies to. Okay, we're getting there. Finish this. What's the next one? X to the fourth times x to the 1/2. Plus what? X to the fifth times x to the 1/2. Plus what? X to the sixth times x to the 1/2. Plus x to the seventh times x to the 1/2, right? Let me ask you this. Every term is separated by a plus sign, right? So like x to the third times x to the 1/2 is one term, okay? X to the third times x to the 1/2 is one term. Each of those are terms. What is common to all those terms? What is common to all those terms? What is the same in all those terms? To the 1/2. X to the 1/2. You can factor out an x to the 1/2 power, and so your answer is going to be, if I factor it out here, what's this one? Nothing. It's not nothing. 1. Plus, what's left here? No, x. Plus what? X squared plus x cubed plus x to the fourth plus x to the fifth plus x to the sixth plus x to the seventh. That is simplified. That's your answer. For all of you guys who are going to be math majors someday, you'll love doing those problems someday.
Don't racist.
Hey, Jacoy, there are a lot of people who love math.
Just sit here and just.
Jacoy, what do you like to do? Do you think everybody likes to play sports?
Yes.
Okay, not everybody likes to do what you like to do. Some people like to make math. Did you know that if it wasn't for people who like to do math, we wouldn't have all the technology we have today? We wouldn't have all the technology we have. Hand me your phone, I'll burn it. Hand me your phone, I'll burn it. You just said that. Okay. Hey, what if we just all got rid of our phones? How many of you guys would be okay with getting rid of all the cell phones and iPods? Okay, hey you guys. Let's bring this together. Okay? Okay, the first person in this task, Chandler, she explained that she went how did she say it? 12 miles per hour, right? She went 12 miles per hour. And the second person described, Isaac described, he went okay, he said that he bikes a 5-minute mile, right? 5-minute mile. Well, when you guys did this, you found out that the first person, we did really all that was happening is Chandler was figuring out her speed by using a function, distance as a function of time. So she went distance is a function of time. So that we write d of t, and t was our independent variable. I think everybody got this one. What was our equation? 1/5 t, right? In other words, we can put t, and t represent, what time frame does t represent? Does it represent hours? Represented what? Minutes, right? So we put minutes in for time, times it by 1/5, and we figured out how far of a distance she went, right? Any questions on that? I want all eyes right here right now, you guys. Okay? So that was the first one. Now, Isaac, he calculated his as time as a function of distance, right? And what did we come up with for his? 5d, right? So you see, the first one, the independent variable was t. The dependent variable was d. And then the second one, the independent variable was d, and the dependent variable was t. Do you understand that? Okay? This is what's known as an inverse. This is what we know as an inverse. Is when these two, we found out that these two both actually go at the same speed, don't they? They both traveled at the same speed. It's just that one calculated distance as a function of time, the other one time as a function of distance. And that's how they were calculated. I've run into this before where people do that. I mean, they want to know, okay, how fast do I have to run each mile to run the marathon in 4 hours? Okay, I've heard them say that. That's this one right here, right? And other people calculate it, well, I can run 6 miles in 1 hour. So they're saying I run 6 miles per hour. But then you have to figure out how long that's going to take to run the 26.2 miles. So anyway, it just depends on how they're calculating it. But these are known as inverses right here. Couple of things. I have not run a marathon. My wife's run 9 of them. So 9 marathons. She's run her 10th marathon this year. I think I might do the marathon this year with her. We'll have to see. So I've been starting to train a little bit. So. Huh? There's been I think 2 of our marathons I didn't go to, but I've been to the rest of them. So, all right. So, what we're going to do right here, you guys, I want to talk about how inverses work. When you guys graphed these, when you looked at the table of values, when you guys looked at the tables, what did you notice? I want everybody to look at the 2 tables, compare them. What do you notice? They're switched around. The x and y switched around, right? Grant, that was a very important point. Listen. The x and y switched around. In fact, I want everybody to write this down. Definition of an inverse. Write this in your notes. Okay, definition of inverse. Switch x and y. In other words, the domain and range switch. You'll notice on the first one, we used as the domain, or the independent variable, we used time. And distance was the dependent. And then we switched them on Isaac's method. D was our independent variable. Time was our dependent variable. And that's all an inverse is. That's a pretty easy concept, isn't it? Okay, one other thing. I want to talk about the graph. What did you notice about the graph when you graphed them? Anything you notice about the graph?
Similar.
Huh? The domain and range switched, but there's something significant about it. Say that again? The slope flipped, exactly. One was 5, and what's the reciprocal of 5? 1/5. What happens, you guys, if this is the line y equals x, you guys all understand what the line y equals x is? It's a line, slope of 1, goes through 0, 0. It's on a 45-degree angle, right? This is critical to understanding. All eyes got to be right here, you guys. Okay, critical to understanding. When you graph these, what happens is they become, both of those graphs that we just did went through 0, 0. That's why I'm writing these like this. They are reflections over the line y equals x. I want everybody to write that down. And inverse functions are reflections over the line y equals x. So you're going to write inverse functions are symmetrical over the line y equals x. Okay? Inverse functions are symmetrical over the line y equals x. Very important to know that. Raise your hand if you know which variable is the independent variable. Which variable in any function is the independent variable? The x, right? And dependent is the y. Okay? So know that. Did only really 4 of you guys know that? Or the rest of you guys did not know that? Or?
I knew it.
I was thinking you guys knew that. Okay. Identify the relationship of a function and its inverse. That's what we're going to do next. Okay, so I want to show you a couple of problems right here. Let's say that I am given this problem right here. Y equals 2x plus 8. Okay? And I'm going to write that as f of x. Okay? I want you guys to find the inverse. Here's the notation for inverse. Everybody write that down. That is the notation for inverses. Okay, you pronounce it by saying f inverse of x. I know it looks like an exponent of -1, but it's not. It's not an exponent of -1. That f, that means it's the inverse. I don't know why some mathematician a long time ago decided to use that little -1 that looks like an exponent as the notation for the inverse, and so everybody always thinks of it as an exponent, but it's not an exponent. I want everybody to say it. I'm going to say it and then you say it. F inverse of x. One more time. F inverse of x. So when you say it, that's how I want you to say it. Just get in the habit of saying it that way. F inverse of x. Okay, how do you find the inverse? How do you find the inverse? Everybody write that question down in your notes. How do you find the inverse? We've already talked about it. You guys told me. Jacob. Take the opposite of the slope. Well, that kind of has something to do with it. However, I mean, that's what the slope's going to be, but there's more to it. In this one, since it has a y-intercept of 8, what else do we have to do? Think about what happened between those two problems. What? Okay, we got to reflect over the y-axis, but there's a simpler way to do it. Branson. You're not raising your hand? Okay, Christian. Oh, you started saying something.
You gotta find the reciprocal.
Well, some of you guys are saying find the reciprocal. That the slope is going to be, the reciprocal of 2 is going to be the slope of our new function. But there's something else that happens that's easier to do. I told you, what is an inverse? Right back here, definition of inverse. Look at it. Switching the x and y, right? So how could I take this problem right here and find the inverse doing that? Yeah. Okay, I'm going to change f of x to y right here. So y equals 2x plus 8. How can I change this equation so I can find the inverse? Switch the x and y. That's exactly right. That's the definition. Now, I have to solve that for y. How do I solve that for y? Minus 8 from both sides. I would get x minus 8 equals 2y. Then what? Then divide by 2. So I would get 1/2 x minus 4. Y equals 1/2 x minus 4. And then the last thing I want to do is change it to inverse notation, which is right over here. So f inverse of x is equal to 1/2 x minus 4. That right there is the inverse of this one right here. Okay? Finding the inverse. So there's 4 steps I always teach all my students to finding an inverse. You guys ready for them? Number 1, replace. Replace f of x with y. What do you think step 2 is? Switch x and y. Good. Switch x and y. What's the next step? Isolate y, or solve for y, however you want to say it. Isolate y. Good. What's the last step? Use inverse notation, right? Use inverse notation. Technically, after you switch x and y and you isolate the y, you have the inverse, but we put it in inverse notation. Okay? So 4 things. That's pretty simple, isn't it? Okay? Do you think you can do that? All you have to do is switch x and y. Okay, now, your assignment today is about inverses. But they always have some stuff that goes back and reviews, and also some stuff that's going to introduce what we're doing. I don't think I need to explain anything on here. I think you guys can figure it out all yourself. Okay, let me just ask you this. On a square, if you're given a square, and you know the length of one of the sides, or no, if you know the area, let's say you know the area is 64 square inches. Can you figure out what the lengths of the sides are? 6? 8. There you go. It's 8. Why? Yeah, it's 8 times 8 is 64, right? You understand? So you're going to need to know that for your assignment. All you have to do is take the square root of the area, right? To find the length of the sides of an area. Okay, I would write that down in your notes in case you need to know. Okay? Now, I think that's it. I think you guys have everything. I'm going to hand you the assignment.